Good afternoon, everyone. Just going to do a quick sound check before we start. Rosie, can you just confirm we're live? Good. Okay, I'll make it 2 minutes past, so let's go.
Hello everyone, and welcome to the Introductory to Telemetry webinar. My name is Jess and I am a project manager at Van Walt. My department is responsible for all things telemetry, so that ranges from designing bespoke telemetry networks to building the equipment to installation and after sales care.
Good afternoon, everyone. I'm David Van Walt. I'm the director here at Van Walt Limited for the group. One of my roles is to support Jess with telemetry. So I focus very much on site visits. So the design and the pre-requirements phase for anything to do with networks that we're installing. And I also deal with a lot of the installs. So I'll go to site, install systems and also maintain them as we go through. So that's a big part of my role here.
So today is an introductory to telemetry. Just to let you know that we are being recorded, and the topics that we're covering today are what is telemetry and why do we use it? How does it work? Building a system, things to look out for, challenges that come with it, and some examples at the end. So we've got a tight window today, so we might not be able to cover everything. So further information can be found on the Van Walt website. There's lots of resources on there that'll be really useful. In a minute, our email addresses will be popped up on the chat, so you'll be able to contact us by email, myself or David, or give us a call, and we're happy to have a chat about any requirements that you may have for telemetry. As I mentioned earlier, we do have a limited time today, so any questions, please pop them in the chat and we'll respond to them after the webinar. So today we're going to be covering an introductory to telemetry. So there's a lot to cover and there's a wide range of options, but we're going to mainly be focusing on what Van Walt offers. So we're going to start off with what is telemetry and why we need it.
Okay, thanks, Jess. So I'm going to kick off with why we use telemetry. But before we look at that, we want to look at the three ways that we take measurements today. So there's manual ways of taking data recordings of whatever parameters it is that you may be looking for. We've got loggers, which is a semi-manual process, and then we've got telemetry, which is the fully automated. So just to walk through those, I mean, everyone here is probably familiar on the call with things like water level dip tapes or handheld multi-parameter songs. This very much is someone puts that in their car, they drive to site, they take a measurement, they record that measurement, they go home, and then they record that into a database for interrogation or use. Second most common way of doing it is using something like loggers. So this here is a level scout, and on the level scout or any other logger, you would define a frequency of measurement. You would set that to record for a period of time. You would deploy it. And then after a period of time, maybe a week, maybe a month, you go back to site and you retrieve the data from the logger via connection to your phone or to your laptop, take that back to the office or home, ingest it into your databases, and then interrogate and use the data. So as I said, a semi-automated process. And then the final one is telemetry, which we're going to look at a little bit more today, where you deploy an in-situ, an on-site installation. You leave it there for a period of time, normally for a fairly significant period of time with telemetry, and that data is relayed back to your phone or your desktop. So you log in with your username and password, and you've got all of the parameters that you're measuring readily available on your site. So those are the three most common ways of getting data. So they all have advantages, they all have disadvantages, and they have different costs. So what I want to run through now, I'm going to bring up a slide, is how do we determine where we use telemetry and where we don't? And there's several factors that we need to consider when we're doing that. So I'm just going to bring up the slide, and we will start with slide 2. Is over here. So what are we looking at here? So the most common factors that we need to consider with telemetry are, the first one is frequency, and we're going to go through each of these one by one. But frequency, how often you need to measure, the cost of those measurements, criticality, what is the data and why is that data critical, or how is that data critical? We'll look at the consistency of measurements, access, integration with other systems, and then also the confidence that you have in your system, that it's working and that you're getting the data that it is that you need. So I'm going to start off, take those one in turns, and the first one that I'm going to look at is frequency, and frequency is the speed at which you measure. So it could be once every 5 minutes, it could be once an hour, it could be once every 15 minutes. It doesn't really matter. It will map to the requirement that you have. Now there's two different ways of summarizing this, and we determine those as spot versus continuous monitoring. So spot monitoring, very much a point in time. You can get basic trends, but it can be difficult to relate to specific events. So what I've got on screen here is a real world example. This is a live system for one of our customers that's allowed us to share this data. What we're monitoring here is water level, groundwater level below the surface of a road. Top line there is ground level, and the blue line is our telemetry system. It's monitoring once every 5 minutes, and you can see there we've got a downward trend, but towards the last couple of days we've got 2 spikes. In this particular case, those spikes are what is important to the project. Those spikes are what it is that we're looking for. They're showing a response directly to rainfall, and they're showing a response as to what's happening below the surface of the road. Now, the red dots that you can see on the chart are where I've put in spot monitoring. So these are manual measurements that are being taken once a week. Now, in this particular example, I've made those measurements up to overlay to articulate the point. But you can see if you take spot measurements once a week, in this scenario, you actually miss your 2 spikes, which is the data that you're actually looking for. So this is a great example as to looking at the project, what the requirements are, and looking at, well, actual manual monitoring is not appropriate for this scenario because I need the high frequency of data. I need continuous monitoring because if I don't have the continuous monitoring, I'm not going to be able to see the spikes, which is what I'm looking for. It's also the difference between a logger. So we had the standard level scout there, and telemetry. With a logger, you install for 3 months. You go back, you retrieve it. In this case, there are events and activities based off of these spikes. If you don't see that data in reasonably good real time, you can't make decisions, you can't take remedial action. So putting a logger in place and retrieving it, it's too late. You'll see the information after the event has already happened. So, it's a really good indication as to where you would use telemetry and the sort of data that you might miss. If I look at the second example that we've got, so this is an example from a system that we have in New Zealand. So this is monitoring nitrates within water. And you've got 2 lines here again. You've got the blue line, which is our telemetry system, and you have the yellow line, which are grab samples, which have been done on a monthly basis. And what you can see here is the blue line shows you 3 different events that your grab samples have failed to identify, and that's all to do with the timing of the sample. But had we just done grab samples, we would have missed those 3 events, and we would have been unable to tie them back to what actually happened. So again, a great example of where spot and continuous monitoring, you need to really define what it is that we need, why we need it, and what sort of events that you're looking for, because you might find that it's the telemetry that will give you this information. And this is an example where it was actually a fairly late addition where we added the sensor, and these were events that were never before seen. And the only reason that we're seeing them is because we've got that continuous monitoring in place. The second consideration that we had on the cycle was around cost of monitoring. So let's look at the cost of monitoring, and I've put together a very high level and basic scenario here for telemetry, very much people versus technology. So the scenario that we built here is I want to monitor water level. I'm going to relate that water level to a datum. I'm going to do it weekly, one location, and that location happens to be 50 miles from my office. So 50 miles is around about a 3-hour round trip, hour to get there, hour to do your sampling, and an hour to get back again. So taking some very basic costs, and I appreciate these are very basic, but it's just to illustrate the point. Minimum wage in the UK, £11.44. Mileage rate currently set in the UK is 45p a mile. If you equate those costs over 3 hours with the driving, not taking into account anything like depreciation, hire of vehicles, employment costs, you're looking at around about £80 per site visit to take that one reading. If you look at the chart, I've plotted that as the blue line. So to start this particular project, it's a very low investment, £80 to get someone to site. But as you can see, as you go through the life cycle of the project, and I've got 24-month life cycle on this particular chart as an illustration, you can see the chart, the cost rapidly increase. And actually, at the end of the 24 months, you're around about the £7,500 raw mark for the cost of that sampling. The red line is telemetry. So I put in a basic telemetry system. I've also included site visits once a month and the ongoing run costs. And you can see you have a higher initial investment, but it's actually a fairly flat line, so easy to predict the costs. It's a consistent measurement. It's you're getting more data than you need, but effectively what it's showing you is that in this particular scenario, at 5 months, you're cheaper running telemetry than you are sending someone to site. Now, really, really important to state, I'm not saying we replace people with telemetry. What I'm saying is that we look at the cost of telemetry and the opportunity cost of the person going to site, all of the other hidden costs of that person going to site, and looking at can we use their skills and their resources in a better way, because we're getting the data in a consistent format, and after 5 months, I'm actually regaining the cost of going to site. And actually, over a 24-month period, you've got a significant difference in the cost of having deployed someone to site. So again, a key factor when determining whether you're going to use telemetry or whether you're not. It's not quite as black and white as I put there in the picture, but it gives you a really good indication as to, yes, it's more expensive at the start, but we need to look at the long-term effects. When we look at long-term, we talk about cost of ownership quite a lot. Cost of ownership for a telemetry system here, we would estimate between 5 and 7 years is a good life span for a telemetry system. So that's your cost of ownership. So you should be looking at the cost of the full 7 years and breaking that down, and that's a really good indicator as to projecting your budgets and projecting your costs of the projects that you may be running through. The next point, which is really important that we need to consider for telemetry, is criticality of data. So I've got a little chart here to summarize. What is data? What makes it critical? Why is it critical to you? Why is it critical to your project or decision making? The easiest definition is the cost to you if you don't have it. What happens if I don't have my data? If I don't have my data, what is it that I can't do? And that's the important question. What is it that you can't do? And that will determine the type of system that you need to implement. So at its lowest level, data can be research projects. It could be a feasibility study. What's the cost of me not having that data if I need it on Monday morning? Yes, it's going to be a headache. Yes, it might cause me a few issues. But is it going to grind my project to a halt? Is it really going to grind the feasibility study to a halt? There's probably ways around it. Probably not. On the other side of the scale, you've got life scenarios, flood defenses. If I don't have my data, I'm ultimately putting people's lives at risk. You can't put mitigations in place. You can't turn pumps on. You can't potentially evacuate people. That's critical data. If you don't have that data, you can't make a decision. And if you can't make that decision, there are severe consequences. So again, there's a scale of how critical that data is. And it's really important because the more critical that data is, the more robust your system needs to be, the more you need to start thinking about things like redundancy, risk assessments, and that all feeds into telemetry because quite a lot of that is done in a telemetry system, which will get you that data to enable you to make those decision points. One of the things as an indicator I've just drawn down here is, assessing data is a very simple way of looking at might move from manual processes to telemetry processes. But taking our flood example there, you assess risks by impact and urgency. So let's look at flood data. How urgent is that data? Well, it's very urgent. If I don't have that data, I can't make decisions, and I need to make those decisions quickly because there may be actions that I need to take. So from a flood perspective, the urgency of my data is critical. So, I'm over in the number one bucket. It's critical that I have that data. What's the impact of not having that data? If I don't have that data, I can't make the decisions and we have a potential flood risk. So the impact of that data is also critical if I don't have it. So if you follow the matrix along, it puts you very much in the bucket of, you really want to be looking at a full telemetry system here. It will get you the data, it will get you the data quickly, and you can make the decisions quickly. So, it's a perfect candidate for telemetry. Let's look at another example. We'll look at a mine that has or requires consent to use water for mining, and they have to provide a report to a regulator to make sure that they're within the boundaries of their water usage. And if they don't, they have financial penalties, or they could also potentially lose licenses. They're fairly significant consequences. But the key here is they need to submit this on a quarterly basis. So from an urgency perspective, you could argue that the urgency of that data is less, so maybe 3 or a 4, so it's a medium to low, because if you don't have it on day one, you've still got time to recover, use alternative processes. It's not urgent that you have it on day one. It becomes more urgent as you go through, but the initial urgency is less. The impact, however, remains high, because if you don't provide that data, there's a potential significant fine, or there's also the potential that you lose your license, which is also significant from a mining perspective. So the impact remains high, but if you follow that along the chart, you're more in the kind of the manual logger territory. So for that particular scenario, maybe manual measurements or logger measurements are sufficient to meet the compliance requirements of that particular scenario. It's only one factor, which these all have to come together, but it's a good indication, it's a good idea to look at where you might separate telemetry from logger, straight logger, and manual mechanisms. Going back to our cycle, it's here. We want to look at consistency. So consistency of measurement. So this is where telemetry is very good. A telemetry system is generally fairly consistent. You deploy a system in the field, wherever that may be, that system doesn't move. The sensor doesn't move. So every time it takes a reading, it will take a reading every 15 minutes or every 30 or whatever you've set it to. Every 15 minutes on the dot, it takes a reading. It takes a reading from the same place in the same way and sends the data in the same format to the end location. There is not much that can change in that chain of command, which is really important. We're not introducing error. If you give that to an individual, human error can creep in. We all have processes that we follow, but we run a training course here every quarter. One of the exercises that we do for fun and to illustrate the point is we send all the delegates out with a dip tape, and we ask them to take a water level reading. And every course we come back and we have a fluctuation in the readings that have been taken, sometimes in centimeters, sometimes in meters. And that comes through lack of process, or they're rushed, or they're looking at someone else. Someone's measuring to ground level, someone's measuring to top of well, someone's measuring on the left side, someone's measuring on the right side, someone did it at 10 o'clock, someone did it at 12 o'clock. What we've done is we've introduced variables, and variables introduced errors, whether it's following a process or not. It introduces errors, so your data is never going to be as consistent as a logger or a telemetry system. Consistency is a massive benefit of telemetry. You can be sure that the data that you're getting is representative of the setup that you did at the start. Access, how do we get to site? Some sites are easier to get to than others. Some sites are very, very remote and very difficult to get to. And other sites are easy to get to, but there's restrictions. For example, a railway. You can't just get onto a railway track to take recordings. You need to book slots, and those slots are likely to be overnight. And you'll probably get a window of 2 or 3 hours to do that work. So it's actually quite difficult to get to that site on a regular basis. You may have sites that are very remote islands. Again, difficult to get to, expensive to get to. So again, telemetry there, wins the game. You deploy there once, you get your data. You don't have to go to site as often, and again, that's a massive advantage from a telemetry perspective versus the manual or the logger. Integration. When we talk about integration, I'm talking about systems talking to systems. So we all run our own internal databases, we all have our own systems, and we all have our own way of writing reports. When you have manual measurements, you'll manually record those and then put those into some sort of database or system, and feed other systems into that to build your overall picture. So manual overhead is intensive. It can be slow. Again, you're opening it up to errors. With a telemetry system, you normally fire everything into a central server. That server has the capability to automatically distribute data to your own systems, to external systems, to regulators. You can put in routines that share that data in a certain format, and a consistent format. But you can also start joining data together. So you may take data from your servers, so from your sensors, and you may then also take data from the Met Office, and you may take data from another scenario. The system will bring all that together in an automated fashion, enabling you to interrogate and make decisions based on that data. And then the final one on this cycle is confidence. And by that, I mean knowing that we're going to get the data that we need to do the project that we're working on. So the downside of a logger is you deploy it to site, you return 3 months later, or whatever the frequency is, and you find out that you forgot to turn it on, or there's been an error, or it's been stolen. You don't find that out until the end point. At the end point, it's too late. You've lost that period of data, and if that's 3 months, you've lost 3 months worth of 3 months worth of data. Only scenario you've got there, if you don't have redundancy, is to start again. With telemetry, you have the confidence that it's working. The reason that you have the confidence that it's working is because you can see that it's working. You can log on every day. You can see your data. You can set alarms. If your battery is running low, you'll get an alarm. If it hasn't uploaded for whatever reason, you'll get an alarm. If one of your sensors is losing its calibration, you can get an alarm. If the sensor's dirty, you can get an alarm. So you know that there's a problem before you need the data, and you can build that in. So the telemetry is not just about getting you your raw readings for the parameters that you're looking for. Telemetry is also about ensuring that you get that in a consistent and a reliable manner, and telemetry enables you and allows you to get that information to be confident in the data that you've got. You're confident that it's installed, you're confident that it's in the same place, you're confident that it's working, therefore you can be confident in the data that's returned to you to make your decisions, and there's far less risk of errors being introduced via different people, different processes, or bringing in different formats together. So those are the key considerations for monitoring, and encourage when we're looking at this, we look at all of the consequences for all of these boxes. You bring them together, and that will really very much define the type of network that you want to put together, the type of processes, how it's going to benefit you, and ultimately, does it give you the results that you need to have to build your system and to run your project. Okay. The next part that I would like to talk about is how it works. So I'm going to talk a little bit about what a telemetry system is in terms of its construction, and what all the components are, where the risks are, what all of them are doing, and just provide you a very high-level overview of what actually makes telemetry, and really separate the bits that you don't need to worry about to the bits that are actually quite simple, and how you build that network. So just moving forward to very high-level snapshot chart of what makes up a telemetry system. And I'm going to go through these one by one, but you have a sensor, which will take a measurement recording. You have a controller or a logger, which will power the sensor and do the activity. You have a gateway, which will send that data somewhere. And then you have software, which will enable you to interrogate and report that data. So I'm going to run through those one by one. I'm going to start with the sensor. Now, there are many, many different sensors. We'll talk about some of those in a second. But sensors talk in different languages. And it's important to recognize that, because some systems are single language, some systems are multi-language, and some just won't work together at all. And it's really, really important that we understand that when we're building a system. Now, when I talk about languages, I'm talking about the language that the sensor uses to talk back to the logger. There are three main languages that we use here for the sensors: SDI12, Modbus, and Pulse. And I just want to run through each of those three, what they are, what they do, and the kind of the advantages and disadvantages, and how we use those. So SDI12 is probably the most common language used with environmental sensors. It's a very easy language to use. It's also quite a simple language. Very straightforward commands. You issue a command from your logger in one direction to the sensor to say, wake up is command 1, command 2 is warm up, command 3 is take my temperature reading, and command 4 is send it, and command 5 is go back to sleep. And that's kind of the structure of SDI12. So very logical and simple block commands that you use to power up and to use. Advantage is simple. Very low power, doesn't need a lot of power to run. But the disadvantage is it's not very flexible. So you have your block commands, they are what they are. They're very easy to interface into systems, but they're not that flexible if you want to control the sensor a bit more, tune parameters, maybe do some calibrations and things like that. It becomes a little more inflexible. So that is one downside. The other two downsides are you can run multiple sensors to one telemetry unit, and you address those sensors with SDI12. The more you have, the more chance there is of interference between the two. And there can be interference on, it's not quite as, generally it's pretty stable, but you can get interference, and that will be represented in data spikes or troughs. And the other main disadvantage of SDI12 is cable length. So if you're using an SDI12 sensor, you should be looking at around about 65 to 70 meters as the maximum cable length you're going to get. So if you're in a particularly deep borehole or you need to run a very long cable beyond 65 centimeters, you are probably not using the right technology, and you want to be using a sensor that uses something that's not SDI12. So that is a big downside. Modbus is the second. So Modbus is a far more flexible language than SDI12, but it's also a little bit more difficult to use. It enables you to do more complex command strings. You can tune sensors. You can build more complicated routines as to how a sensor is going to measure and how it's going to work with other sensors that may be on the same network. So it's far more flexible. In our experience here, it's actually better at power than SDI12 as well. So we do have a slight power advantage, and we can also use some of that flexibility to tune the amount of power that's going to a sensor. So, much more flexible, and that's kind of good for us when we're building systems. It's much better at managing interference, so far more stable. There's far less things that can interfere in the signal between the sensor and the logger. And one of the major advantages with Modbus is the cable size. We can go to well in excess of 1,500 meters without any problems, which is great for particularly deep boreholes or where you've got to run very long cables. So big advantage of Modbus over the two. Disadvantage is complexity. You need a little bit more knowledge of how to use it. And the other disadvantage with Modbus is there are different flavors of it. So whereas SDI12 is SDI12, Modbus, there are some versions that have slight tweaks in terms of how they operate, and that can cause a few challenges when you're programming units that use two different versions. The final one is Pulse that we mentioned. Pulse, very, very simple, used particularly things like rain gauges and inline flow meters. effectively it's just counting events. So with a rain gauge, a tipping bucket, for example, every time it rains, the bucket tips. Every tip is a pulse, and it sends an electrical signal back to the logger, and it counts the number of signals. Now, each signal for a rain gauge may be 0.2 millimeters. So you count how many ticks there are, and then you sum those ticks, and that gives you your rainfall, and the same with flow. Very simple to use, very, very low power, and most common with rain sensors, rainfall and those are the three key languages that we use. Why is that important? It's important because it's important to marry that to a system. Some telemetry systems will only focus on one language or the other language. Some will do all, but it's important that everything talks in the right language. The systems that we have don't care. We will use all of them or none of them. So it's important that you understand what they are. It's also important that some sensors you can't change. So I've got a sensor in front of me. It's a water level sensor that only runs a Modbus. Modbus full stop. There is no other language for it. You have other sensors that you can choose what you want to use, or you can have a combination. So it's important in the design to understand what it is that you're doing so that you get the right sensor at the right language to talk to the right system. The next thing on sensors is parameters. So let's talk about parameters. But there is no limit to parameters. If you can measure it, we can do it. So there is probably a sensor for every parameter that there is. It's a case of finding the sensor, understanding the language it's talking in, and configuring it to the telemetry unit. So parameters with telemetry should not be a hurdle. Everything is possible, and that's the mentality that we use. Everything is possible. There may be consequences of doing that, but we start with everything is possible and we work from there. So for parameters, pretty straightforward. Everything is available. What is important with sensors, and I'm only going to touch upon it very shortly because it's more about telemetry, but just from a sensor perspective, is sensors come in all different sizes, ranges. There's millions of them available, and they're from very, very cheap to very, very expensive. When we build telemetry networks and we look at sensors, we have to make sure the sensor is appropriate to the job that you're doing. One of the key things around that is accuracy and precision. I'm just going to touch upon this very, very quickly, but sensors aren't the same. A very cheap sensor that monitors water is not the same as a very expensive sensor that monitors water. They use different technologies, different ways of doing it. One is more reliable than the other. Generally, they're all pretty good, but you've got to map it back to your requirements. Great example here on the screen here, which I've stolen from a course that we do, but precision and accuracy. Every sensor that you buy will have in the manual precision and accuracy figures that they state. Good accuracy, good precision on a dartboard, you hit the bullseye every single time. Poor accuracy, you're missing the bullseye, but you get all your darts in the same location, and poor accuracy and poor precision is you're all over the place. Now that may be acceptable depending on the constraints of your project, or it may not be acceptable. So really, really important that you understand, and we all understand, what sensors we're using. The telemetry system probably won't care, but your project will care, because ultimately the sensor is what is providing you the data. It's not the telemetry system. The sensor is the part that gives you the numbers, and all the telemetry system is forwarding that onwards to your server for you to digest. So really important sensor choice, absolutely critical that we marry that. And that's one of the first requirements. What are you measuring and why are you measuring it? Get the sensor right, and then everything else follows behind it. Don't start with the telemetry system and work back to the sensor. Otherwise, you'll compromise when you get to the sensor, because the telemetry system will say you can only do this or you can only do that. So always start from the bottom and work your way to the top. So dealt with sensors. Let's move on to the controller and the logger. So at this point in time, we're not in full-blown telemetry. We can still be standalone. It's when we add the gateway that we become full telemetry. But controller logger, what's the purpose of the controller logger? Well, the purpose is to talk to the sensor. It tells the sensor, hello, wake up, take a measurement, give me the reading, go back to sleep. That's what the logger is doing, and it records that, ready to transmit to wherever you need it to go. So let's look at what we do. Different ways of doing it, radio or direct wired, generally influenced by power and the site that you're on. We use a logger, and Jess will cover this a bit later on, that uses radio frequency. It uses a FLEC radio chip, runs on a very narrow band of the frequency, which reduces the number of interference. It's license free, very low impact through noise, so very, very stable, and very, very low power, run by 2 small AAAs. All it's doing is it's telling the sensor to wake up, take a reading, and it stores the data, and then it relays that data via a wireless signal to a gateway, and we'll show that in a second. The advantages of that is it's very, very small, it's independently powered, and you can put it things like under roads, in buildings. Radio frequency can travel through walls. Cell reception sometimes cannot, particularly if you're under the road or in a cave. Radio is a far more stable signal to get that information out to a gateway to you. So we use radio. You may have heard of technologies like LoRa or long range, which uses a very similar principle, slightly different way, normally under some form of license, and uses a slightly different part of the wavelengths, but effectively the same thing. But all it's doing is relaying the data from your sensor out to the gateway. You can also wire directly into a controller or a logger, and we'll explain that in a second. Moving on to the gateway, which is the third one. So the gateway, the sole purpose and life of the gateway is to send the data that it's recorded to a location, and a location is usually a server, which can be a physical server or a virtual server or in the cloud. In our case, we use a cloud server, but the gateway is using a technology to send to that server. Different technologies that are available will have advantages and disadvantages. Some use more power, and some we use a combination of. Most common ones at the top, the lowest power one is IoT, which you may or may not be familiar with, but IoT is effectively machine-to-machine communication. It's 2 machines talking to each other without any other intervention, and those 2 machines can talk to each other over any form of communication, whether that be Bluetooth, Wi-Fi, GSM, satellite. It's effectively the machine talking to a machine. In your homes, the most common things to liken that to would be something like your Ring doorbell. The Ring doorbell is talking to your Wi-Fi, which then sends a signal to your phone for you to see if there's anyone knocking on the door or walking past. It's the same type of technology. It's jumping onto that capability. Very low power, very simple, machine to machine, no human intervention. So very quick transmission with nothing in the way. Behind that, you've got the cell communications, which you may be more familiar with. So 2G, 3G, 4G, 5G is currently in existence today. 5G being the fastest and very much designed more for data. 2G was initially designed for text, 3G came with data, and then we moved to 4 and to 5. 2G and 3G are being decommissioned. So in the UK, at least, 2033 is the date that has been set for the full decommissioning of those services. And we've already seen, particularly on the 3G side, those start to disappear from the networks. Normally you cycle through more than one. So again, our modems are currently working on 2G, 4G. We will start with 2G. If that connects, great, that's all we need. If it doesn't, we switch to 3G, and then we go through there. Each one is slightly more power intensive than the one before. Satellite, so we like Iridium, it's what we're using on this side. Satellite is using a chip directly to the satellites, so we don't go via any towers. Advantages of satellite is coverage is pretty well total. There are some gaps here and there, and occasionally you have to wait for a satellite to pass, but generally very, very good coverage. Downsides to satellite are still relatively expensive compared to the others, particularly on data. The more data you have, the more expensive it gets. You do have those black spots occasionally. The other disadvantages are it is still line of sight, so you can't put a satellite under the road, for example. You will need some sort of station above the road to have visibility of the satellite. Other technologies, direct to cell. So that's something very much that Starlink are looking at. So that's your effectively cell signal directly to a satellite bypassing cell towers. So again, you get that really good range of visibility. And what you don't get is the interference of cell towers or the fact that you need to get to a cell tower. So that's a technology that's rapidly increasing. And I put here on the slide future, and that's because this technology is changing every single day. Satellite is getting faster for data, it's getting cheaper by the day, more available, easier to implement, and there'll be more technologies that come behind that. So it's a rapidly evolving technology. So from a telemetry perspective, it comes back to that cost of ownership, that lifespan. What we're using today for sure will not be what we're using in 5 years' time. There will be the next form of communication, and it's just getting better all the time. But what is important is that we do have that connectivity. So we tend to work with a cycling through. We'll use multiple technologies, which is good from a redundancy perspective. But we'll start with, for example, IoT, then 2G, then 4G, then satellite. So you're working through the layers, ending up with the most expensive one, but ensuring you get the data, and you can do that in various combinations. Once we get beyond that, we move to the software. So the software is ultimately where your data ends up. And this is probably the most relevant part to you on the call today. This is where you're going to see your data. This is where you can interrogate your data, manipulate it, and make your decisions based on what it is that you need to do for the various projects. So first thing I want to just highlight is telemetry and data don't need to be complicated. And I've just got two examples here. This has come from our server. Again, these are customers that have allowed us to share data. But this chart here, top one is pH, bottom one is redox on the same sensor over a 7-day time period. Very simple to read, 7 days, clear trend, clear pattern, and obviously the raw data is behind it to interrogate to lower levels. But it doesn't need to be rows and rows of data or weird complex algorithms. It can be just very, very simple. Ultimately, it can be what it is that you want it to be. There's no limits here. If you want the chart to be in pink, it can be in pink. If you want to look over 2 months, it can be over 2 months. If you want to look this year versus last year, it can be done. It's once the data is there, you can do pretty well what you want with it. But again, we need to know what we want to do with it so we can display it and get that data format in the right way for you. Second example here is just going to talk about it in a second, is alarms. Again, it doesn't need to be complicated. This is, again, a site that we have. This one's measuring conductivity. You can see the blue line is the conductivity reading, nice and straight through the middle. And then you've got the red line at the top and an amber line. So we've got a low alarm, or we've got a high alarm, but we're right in between the two. That's where we want to be. If we deviate, you can very, very quickly see it on this chart, but you'll also get automated alarms to advise you that you've breached a threshold, and those thresholds you can tune and change. But again, that's done on the software layer, or traditionally done on the software layer, where it's easier to maintain and tune to your requirements. So it doesn't need to be complex. The other thing that we need to consider when we get to the software is comparing or comparison of data. We need to look at, are you just comparing your own data? Are we taking in feeds from other systems? Are we comparing site versus site? So this is where you start the relationships and the logic. And again, this is much easier to do once you've got it in the server. Once it's there, you can manipulate it to your heart's content. And it's really, really important to get that data there in the server to be able to do that. Alerting we've covered. Sharing, again, important. Generally, data is not for one person. There will be multiple interested parties. Again, using the software, you can set up direct feeds for regulators, for example, or you may have customers downstream that need to see things. You can permission what they can see. You can automate data feeds into external systems, use technologies, SFTP, APIs, etc. Very easy, machine to machine, to relay data without manual intervention. We talked about integration at the very start, but it's about enabling the interested parties to have access to the data that they need to see, and they may not need to see everything, but we can automate all of that. And again, with telemetry, that becomes very easy. Manually, it's not so easy. It's possible. It's time intensive. There's a manual overhead. Telemetry, once it's set up, and we do that as part of the requirements, it can go and it's done for you. So your regulators will get a copy of the report every week or every month or whatever it is, and they will get a copy of the data that you want them to get visibility of. So that's very much the software. Now, when we talk about software, we very much focus on the raw data, and I'll talk about that a little bit later on. We'll get the raw data into a visual display. When you want to do lower level things, most customers will have their own favorite software or favorite algorithms. Then we'll offload that data into internal systems via routine to enable them to or to enable you to do whatever it is that you need to do with that data. What does that look like from our side? So 4 systems. Just to summarize, you've got the sensor, which takes the measurement. That's its only purpose in life, take a measurement. You've got the logger, which only purpose in life is to tell the sensor to take the measurement, to record it. The gateway, that's purpose is to send that data somewhere. And you've got the software, whose purpose is to display and enable you to interrogate that data. So 4 very distinct roles, some of which may be merged, but they are 4 very different parts of the puzzle. And again, you can use some or all of them to different complexities. So what does that look like in our world? A quick view of how we do that. So bottom left, working from the bottom left up, you've got the sensors talking whatever language they may talk. So again, we marry the sensor to the project. That will talk to a data logger, which will energize the sensor to say, I want a reading every 10 minutes for temperature. That data logger will send it to a gateway, which is here. Now we're using radio in this particular example, but it can also be a direct cable. In the middle here, Jess will show you in a second, with radio, you can also extend the range. Radio is line of sight. Whilst it can go through walls, it is generally line of sight. So at maximum around about 12 kilometers. But it can be hundreds of meters as well, depending on what's in the way. We can use a relay in the middle to effectively bounce the signal down the line. Great examples we've got on that are a project in a cave where we bounce the signal out of the cave, and also one in the London Underground where we bounce the signal out of the tunnels up onto the platform. And then you've got your gateway. So that's sending over satellite or GSM in this particular model. That sends to your cloud server or our cloud server, and then all of you are down here interrogating that data or getting a copy of that data, depending on how we set that system up. Before I hand back to Jess, just to take you through some of those examples, one thing that is important whilst I've got this chart up is when we're looking at risk and looking at mitigation, really understanding what you can mitigate and what you can't, and what you have control over. And I particularly want to call this section here at the top, the satellite and the GSM towers. We have very little influence over mobile carriers or satellite providers, and I don't think anyone in the school will have a huge amount of influence over them. So the services that they provide, we latch onto. They are very, very stable services, but there's also a risk with those services. So generally we use more than one because if there is a problem, we have limited impact on them. So we need to work around that problem. So, everything here is 100% within our control. Here we have lesser control, and therefore we need to focus on mitigations as to how does that data pass through that point, and what can we do to help that along. I'm going to stop the sharing for a second and hand back to Jess, who will just walk you through some of the solutions that we've got, and then I'll get back to objectives and requirements.
Thank you, David. So we're just going to go through some of our equipment, which you can see here. So starting at the top, the little device at the top is called a Van Walk KISS. That stands for Keep It Simple Sensing. With this device, you can measure water level and temperature, or water level, temperature, and conductivity. So this device will record data every 15 minutes and upload to the portal once per day. So that is a fixed frequency, and it can't be changed. So with this device, it has an internal battery which lasts 2 years, and it's pretty much designed to be plug and play. You connect the sensor, you deploy it on site, and you leave it for 2 years, and just watch the data come in once per day. If you're looking to monitor different parameters, or you need alarms, or just a different frequency, let's say you're monitoring for flood defense and you need your data more than once per day, you would then go for a different standalone logger, which would be this one here. It's called the Vanwalt Data Hub. So the Vanwalt Data Hub, we can connect pretty much any sensor that you like. Can range from soil moisture sensors to flow meters, rain gauges, pretty much anything. So your sensor will be deployed on site, it'll be connected to the device. That has an internal battery, which is kept topped up by a solar panel, or we have the ability to run it from mains if that's available on your site. So we can set the logging frequency to whatever you need. Our standard is 15 minutes recording, and then we upload to the portal once an hour. If you're looking to use this for flood defense, for example, you may want to upload to the server every 30 minutes. If an alarm is triggered, an email is generated and it will go to everyone on the distribution list. So then you'll be notified that there's an event and you can go do your thing. If you've got multiple locations on your site, it could be a bit of an overkill having several data hubs on site. So what we can do is create a monitoring network using this one here. This is our little data logger. We can, again, pretty much connect any sensor to this device. pH, soil sensors, rain gauges, water quality, sons, pretty much anything. So with these little devices, you would have them dotted around your site. You can connect up to, I think it's 32 of these data loggers to one hub. So we can create quite large networks with them. The data logger has 2 internal batteries. They're AA sizes, so readily available off the shelf. We recommend that they're replaced once a year. So the data logger will collect your data from your deployed sensor and then ping it to the data hub. The data hub will then collate everything and upload it to the server every hour. You'll then be able to log on, view and download your data for the portal. If you have a monitoring network, like David had explained earlier, where you're using a data logger in a cave, you can use this device here, which is our relay. So that would sit between your data logger and your data hub, and it just extends that signal. That also has internal AA batteries, so really easy to replace on site. So everything is pretty much customizable, and it's just a case of finding out what you need and designing it to your requirements. That's pretty much it.
Thanks, Jess. So on requirements, going to spend a little bit of time now on defining objectives. So we want to put a telemetry system in place. We want to monitor a range of parameters. So what are the things that we need to look at when we're building those objectives? So let's put up my slide again. Yeah. Yep. Cool. So defining objectives, functional requirements, and non-functional requirements. So I always break it down into functional and non-functional. Functional is what is it that you want to do, and non-functional is how is it going to do it. So you might know that as utility and warranty, but they're the same thing. You will have to define what do you want to do as the first thing, and then we look at how do we do it and the reliability and how does it do it again and again and again. So functional requirements, what do we want the system to do? First question, always, what is it that you want to measure? And that will define the parameters. So you may want to measure, as we said, pretty well any parameter that you like, water, soil, environment, weather. Define the parameters that you want to measure. Once we've got that, we need to understand the functionality of what is it, or where are you measuring? So are we measuring water in a borehole, or are we measuring it in surface water? If it's a borehole, how deep is it? If it's 200 meters deep, you probably now start to work backwards and look at, well, 200 meters, can't use an SDI sensor, so I'm going to need a Modbus sensor. What's the fluctuation? What's the range? We need to, those are functional requirements. So I want a sensor that will monitor at 200 meters. I want it to monitor water level, pressure, and I want it to monitor temperature. The fluctuation is 20 meters. Those are functional requirements, and those start to enable us to build a picture of the type of sensors that we may be able to use for that particular use case. Again, surface water will be another different set of sensors due to it has different characteristics than groundwater. Frequency, really, really important question. Frequency, two things. One is how often are you measuring? And the second thing is how often are you uploading? Quite often we get asked, I would like to measure in real time. Now we have to define what real time is. I like Formula One and I watch it a lot. At the minute, if you watch it on Channel 4 in the UK, you'll have an advert in the middle somewhere from AWS talking about their systems ingesting 1.5 million data points per second from each Formula One car. Now that is real time. That is a huge amount of data, which they're feeding back to their control systems, and then they'll make their decisions and their strategy off the basis of that. But in context, they are running a 2-hour race, and we are running a 2-year project. Do you want 1.5 million data points of your water every second? Probably not. The complexities of just getting that from a remote site into your server, whilst possible, are challenging at best. And what are you going to do with all that data? A car is going around a racetrack at 200 miles an hour. Soil moisture is not changing every second. It's changing in minutes, in hours. More appropriate for real-time soil moisture, maybe 15 minutes every 30 minutes. So real time really needs to depend back to the project requirements and what it is that you're looking for. So that's why we always question real time. What is it? Do you really want it every second? And there are scenarios where you need it every second, but generally, in our experience and the projects that we work with, 15 minutes, that's not a number that we made up. That's a number that seems to fit most scenarios. So important to understand the frequency. And that has a big impact because the more you monitor something, the higher the impact on things like memory and battery, and they all need to be sized. So really important frequency and upload to the server. Also upload to the server. We're currently working on a project at the minute where we need 5-minute frequency, but they actually need the data once a week. So we can monitor every 5 minutes and upload it once a week. That is a huge consequence of the design of the system because the most power intensive part of telemetry is uploading it to the server through the GSM network. So you reduce one, you reduce your requirement for power on the other. So really important functional question. Next two are very much around the alerting and the data. So what alerts do you want? Why is this functional or not functional? It's functional because an alert is a thing. It's on an event or a set of conditions. And there are some systems that do it better than others, depending again on your frequency. But again, it's an important question to ask up front, because if you ask that up front, you will automatically rule out some solutions, and then you can focus on the solutions that will work. Trending and patterns, again, functional. What are you going to do with the data, or where do you want the data? More importantly, do you want that on our server, or do you want that on your servers, or do you want that on someone else's servers, or a combination of all of them? It's a functional requirement because we need to build that into the design. All of them are possible, but we need to understand where that's going. So very much functional. What are we going to do? So we know what we want to do, we know where we want to do it, and we know what we want to get out of it. Those are my functional requirements. I then look at my non-functional requirements, my warranty requirements. Two things here. First one is security. Security, logical and physical. So from a logical perspective, it's all about the security and the transmission of your data. How does your data get from point A to B to C to D? What are all the hops that it needs to go to get to your server? Where do you cache that data? Where do you store that data? Where do you back up that data? All important to understand. Again, goes back to criticality. How long do you need to keep that data for? How long does it need to be visible for? Is it sensitive data? There are some, whilst it might not sound sensitive, there are sensitive recordings out there that need the appropriate security around them. So we need to understand that so that we can apply the appropriate solution to it. Physical security for us is probably the bigger one or the harder one. Physical security is of your deployment. So if you're in a very remote location and deploying a telemetry system, it's probably fairly low risk. I wouldn't say completely low risk, but there's lower risk of things happening. The risk is more likely to be with wildlife or birds landing on solar panels, livestock and playing around with or trying to eat sensor cables. That all counts as the security of your system. There's one of our biggest challenges is around the solar panels and vandalism. Solar panels are very visible. There's only so much that you can do to protect it because it needs to be visible. It needs to have line of sight to the sun. So we try and position solar panels, out of reach or as hidden as we can do realistically without completely blocking its efficiency with the sun. But security is, some of this equipment is very, very expensive. So the more we can put underground, which is where radio comes in really helpful, the better the security. If you can't see it, you don't know it's there, you're less likely to go and investigate. Most of our stuff is not that exciting to look at, but people might pull cables or attach screwdrivers to it or steal the panels. So security is a massive factor of how we design the system, and it's not just about vandalism. It's also about security from cows, rabbits eating cables, squirrels, birds nesting, all that sort of stuff. It all needs to be part of your requirement. The second stage of non-functional requirements is really from a previous career that I had. I call it 4 M's: monitor, measure, maintain, and manage. It's how do you know your system is working? And telemetry is great from this. So I'm not talking about getting a pH value or a soil moisture value. What I'm talking about is how do I know my system is doing what it's doing? So in order for that, you need to be able to monitor it. And by monitoring, I mean, is the battery health good? Is it got a good signal? Is the charging circuit working? These are all parameters that you get back from telemetry, and you monitor that, and that enables you to ensure that the system that you put in place is going to be capable of giving you the data that you need. So, we will monitor battery on all the systems that we've got. We will monitor the signal strength. If the battery starts to deteriorate for whatever reason because the solar panel is blown into the wrong direction, we've got something that we can do about it, but we can do something about it before there's a problem. Alongside monitoring, there's the measurement of those monitoring, and measurement comes back to trending for this particular part. If I monitor my battery at midnight, I get a very different status to if I monitor my battery at 1 o'clock in the afternoon. One, because it's dark at midnight, and two, hopefully I've got sun at 1 o'clock, which means my measurement will give me 2 very different readings. And if I monitor it at midnight, I might think I've got a problem because there's no sun and I have no charge. Whereas at 1 o'clock, I might think it's all great because I've got solar keeping the system going. But if the battery is deteriorating, I don't have that. And that's where measurement and trending comes in. I've got to monitor and record all those points, because that will then give you an indication of the real health of the system and what it's doing from a power perspective and a signal perspective. Manage and maintain. I'll start with maintain. It's the easier one. we still have to maintain telemetry systems. So once it's deployed, you still need to go to site every so often. You need to maintain particularly sensors. Now, some sensors are maintenance free, or relatively maintenance free. Other sensors may need more maintenance. You may have sensors with optical lenses which may need cleaning or they get fouled. So you need to go to site. Now, telemetry will help you identify when you need to do that, because you'll see things like signal parameters start to deteriorate. But you still need to maintain. And I liken this back to cars. If you don't take your car for a service or change the oil, at some point in time, your car's going to get very upset with you, and it's going to break or deteriorate in its capability. It's the same with sensors. The same with anything. If you don't look after something, we shouldn't expect it to work perfectly. These things need to be looked after, and we need to build a plan in how we look after them and understand what the frequency is. Some things need more looking after than others, but as long as we know what that is, we can build that in to the telemetry. So it's not just about installing, it's about the whole network around that installation as to how you support that. And that's very much around the fourth M, which is manage. Occasionally things do go wrong, and things will go wrong at some point. How do you manage that? What are the expectations of that management? Is there one phone number to phone? Are there two phone numbers to phone? Who do you phone? What do you do? What's the response time? If you phone us, do we respond in 1 hour, or do we respond in 1 month? These are all things that are important to the design of the system, to set expectations so it's absolutely crystal clear where the roles and responsibilities are, where the demarcation points are, who can do what, and what the response times are, and what is it that we can do and what is it that we can't do. And that's all about the management of a system. And that, again, is something that we build into how we monitor, manage telemetry systems. It's not a case of deploying something and walking away. It's a case of ensuring that we deploy something and we can support it, and we know how we're going to support it, and you know how we're supporting it, so that we're all on the same page. And again, it comes back to confidence in that data. The final one on this particular piece, before we move on to challenges, is redundancy. Now, redundancy we've touched upon, but it comes back to data criticality and risk assessment. And I'm just going to touch upon it very lightly, but we've got our risk assessment of all our data points. We know our criticality of data. We know where our weak points are. We can now look at identifying if you've got critical data. So I'm going to take the flood defense as the example, because that's the easiest one that we'll all understand. If that system is offline, there's a big risk. So we need to make sure that that system doesn't go offline, or if it does go offline, we've got something else that can take over. So from a flood perspective, and we've got a couple of these installed, more from a health and safety perspective, looking at, we have two systems, but it's not about putting two systems in the same place, because if a lorry drives over one, it will drive over two. So you put one system in one location, and you put the other system in another location. One system runs on Vodafone, the other one runs on satellite. One is using a pressure logger from one manufacturer, the other one is using a pressure logger from another manufacturer. So you start to separate your risks, so that if Vodafone disappeared offline for whatever reason, you know that your satellite is capable at that point in time. If one sensor loses its visibility due to a power restriction because the solar panel has been stolen, the other one can take the load. So that's where you start to assess, where's the criticality of my data? Where do I need it? Where do I mitigate? And what redundancy can I put in place? Got to remember that redundancy is really, really expensive. So mitigations are always better. But if your data is critical, that's what we need to discuss. And that's why we will always have that discussion with you when we're designing networks as well. What is it? What are the consequences of not having the data? Where are the weak points in the chain? And what can we do to fix that? And that doesn't have to be two systems. That can also be a manual solution or a backup logger. There's many different ways of doing it, but criticality, risk, bring them together, and then we can build that into the telemetry system. And again, really, really important to do that on day one, not on day 56. If you build it in at the start, far more efficient. You build it in the end, it becomes more expensive and you're actually introducing risk into your system. So that's why we will always ask those questions. And if we can get the answers, great. If we can't, there's also the opportunity to plan for how we would do that in the future. Moving on to challenges with telemetry. So put on this slide here, the most common challenges that we have with our systems and how we overcome them. Top two, by far, probably 90% of the challenges that we have. First one is power. Power is everything when it comes to telemetry. Generally, you're not plugged into the mains. You're in a field with solar panels. You've got to size the system, the batteries, the panels to the system that you're running. Some sensors are more power hungry than others, and this is where it's really important. Where we talk about the life of a logger, it's quite easy for me to say our logger will last 10 years before you need to change a battery. Yes, it will, but I haven't attached anything to it yet. So the minute I attach my water sensor, which is now got a power, I'm running actually operationally in about 2 years. But if I have two sensors, I'm going to reduce from 2 years to maybe 16, 17 months. If I put a nitrate sensor on there, which has a whole cleaning mechanism routine on it, it's probably going to last for 2 or 3 weeks. So really, really important that we power telemetry with the right power requirements. So we'll always do the assessment of the sensors that you are going to use or that we're going to use. We build in and we ensure that there's enough batteries or enough solar input or redundant supplies to enable you to run that system for the period that you need to run it for. Also, in cases if you're in a very high risk area, you might not want solar panels and you just want to run a battery. Well, we need to make sure that we have enough power and the right type of batteries to enable you to run for a month, 2 months without needing to go to site, without needing that solar panel. So batteries, power, really, really important. If we underspec that, then we're going to run out of power and then you won't get your data. That's also important in the design. We talked about criticality of data uploads. Upload is the most power intensive process in the whole solution. If you reduce that, you elongate the battery. So if you need your data every 30 minutes, fine. But if your data is not as critical and you're happy with it once a year, once a week or once a day, we can reduce that upload frequency, and that will make a significant power saving. Second biggest challenge we have with signal. We talked about gateway, different connectivities, IoT, cell towers, satellite, interference. We have to expect that occasionally signals drop. We have routines within our system that will do retry mechanisms. So we will retry if it doesn't connect on the first time. And in our case, we retry 6 times. If it doesn't work, it goes back to sleep and it will try again the following hour and keep going, and it caches the data until such a time that it gets a signal. It does happen more often than not. With mobile phones, we don't see it happen as probably as we're using it, but it is happening all the time. If you can't get that initial connection, it will retry and again and again and again. And that's where it's really important that we do the site visits. We check what networks are available. We check what technologies we're going to use and make sure that we can get the most stable signal to a tower to get you the data. And that's where the radio comes in to play. We can start to extend our networks, and maybe if we're installing in a valley, we run a radio network and we install the gateway at the top of the valley, and where there is a signal, we can bounce a signal from one to the other to get that signal. Poor installation is a challenge with telemetry. If it's not done properly, it is going to cause problems. That's why site visits are really, really important. We will always visit a site prior to installation, understand local conditions, any particular regulations, unforeseen circumstances, or potential interference from other mechanisms. A great example here is if you're installing in a borehole and there's a production pump in there as well, you need to separate your logger from your pump. Cables will get tangled. There can be interference from the pump against the sensor. So those are all things that we need to ensure we are aware of, and we work around to make sure that there is no issue with the data. Um, Security, we've touched upon stolen equipment, solar panels, very visible, vandalism, stealing of cables. That's a big challenge. As much as we can, we will always hide things. There are things that have to be above ground. There's things that we can put underground. And then there's things like cattle fencing, sheep fencing, bird spikes and rain gauges, that sort of thing to prevent the equipment being damaged, or we will always arm cables and things like that so that people, rather not people, but animals don't eat the cables, which then will have consequences in the data that you get. Under specking, so where budgets are concerned and requirements are concerned, there's a fine line between budgets and requirements, and we understand that. However, we do ask the question as to what's the future use of the telemetry system. If we're starting with water level on day one, is there a potential that in 6 months' time you're going to want to start looking at water quality? And you may not know the answer, which is fine, but you may have, yes, we are going to do that, but it's a different budget or it's a different project or we haven't quite got there yet. If we know that, what we can do is build and design a system that's capable of quick and easy expansion. So again, using our loggers, we can expand the network very, very quickly. But if you don't use that and you go directly into a gateway via cable, and then on day two, you want to attach something else, you're potentially introducing risk. You're going to have to reprogram. You're going to need to put some new chips in it to talk to radio. So you're expanding a system after the event. So it's always better to try and design that in at the start with a view that it's going to expand rather than bolt things on. If you bolt things on, you introduce risk, you introduce error, and ultimately your system becomes less stable. Yes, it is possible, but it's generally a little bit more work and therefore can be more resource intensive and expensive. Fault finding with telemetry. We've talked about telemetry can give you a good indication as to whether the system's operating properly. So it'll give you battery, signal, all that sort of good stuff. It will also give you a good indication on your sensor accuracy. So if you're monitoring the signal strength on things like flow meters or optical sensors, it will give you a good indication as to the health of your sensor. And if you start to see that deteriorate, you will probably see an impact on your results, but you know that there's time to go to site to clean, to verify, to potentially calibrate. So there's a lot you can do with the data. However, one of the challenges with telemetry, and this comes back a little bit to power, if it goes offline, we are blind. It's very difficult to understand why it went offline because there's many, many different reasons as to why. It could have been stolen, it could have been run over, it could have been struck by lightning, the solar panel could have been removed, the cables yanked out. An animal might have eaten a cable. Many, many, many different reasons why something goes offline. Once it's offline, the only way to get to it, the root cause, is to go to the site and take an assessment, a visual assessment, plug in some cables and understand what's going. It is possible in very complex systems to have a right back where you can actually interrogate a system, but then you're getting very, very power intensive. You need redundant communications channels, redundant power supplies. It's a very, very expensive way of doing it. So it's something that we have to accept, but it comes back to ultimately things like service levels, what is the response time, and how quickly can we get someone to site to look at why something's gone wrong. And then finally for me is just a reminder with telemetry. Telemetry doesn't mean you don't have to go to site. We still have to go to site, and it's really important to understand that. We talked about maintenance of sensors, verification. We have to go to site at some point. So it doesn't completely remove that need. It might elongate the period from going to site, and that's where you get your cost savings back. But it doesn't mean you never need to go to site again. But it may change who goes to site. So you may have service levels with partners like ourselves where we may do verifications for you, or we may do flow gauging for you. There's certain service levels that we can put in place in terms of response times and spares and that sort of stuff. All things that we can build as part of the design of a network. For me, the most important part of this is being crystal clear between the two parties as to what we can do, what we can't do, who does what, when they do it, and how quickly they do it. And as long as we're all on the same page and we understand that, then that's fine. And again, that will link that back to criticality and what it is that you're monitoring. Those are really the key challenges and how we address them. I'm going to stop now and hand back to Jess just to take you through some examples of installations that we've done. Just walk through a couple of the challenges with some pictures, just so you can visualize some of the things that I've gone through, and then we'll bring it to a close. So just bear with me 1 sec. I'll get you some pictures up. Yours.
Okay. Thank you, David. Okay, so we're going to go through some real life examples. With this site, our customer wanted to monitor water level for flood defence. So the challenge with this site was public access and solar power. So we had to locate our Vanwalt data hub, which is what we used for this particular project, somewhere where we could get good solar, but also wasn't too visible to the public. So the solution for this one was a Vanwalt data hub, which is this device down here, and a water level sensor. So we're recording every 15 minutes and uploading to our portal Vanwalt Connect every 30 minutes. If there is a flood event, an alarm would trigger and it would send an email to everyone on the mailing list, and they would do their thing. So that's that one. Moving on to another example. So this customer needed to monitor turbidity. So we had, again, issue with public access. There was a high risk of vandalism. The customer needed the equipment below ground. So that ruled out having a data hub and a solar panel. So we had to think of a different solution for that. There was also a challenge with power and limited water level. So some of our sensors are quite power intensive. So if we're using a data logger, which is what we used in this situation, we may need to use an external power pack as well. So what we did in this scenario is we used a Vanwalt data logger with an external battery pack, which was connected to a turbidity sensor. This was all housed underground, and then above ground we had a Vanwalt data hub, which would collect the data from the data logger and then upload it to the portal. Another challenge with this was the limited water level, so we had to mount the sensor horizontally so that we could actually get access to the water. Yeah, that was quite challenging, this one, but
just had a power cut and all our servers are rebooting. So whilst we talk about redundancy, we don't have generators. Currently just using a mobile. So I think we're out of time. So I think we'll just wrap it up. We've got some examples that we can share separately. We apologise. We weren't expecting a power cut, but it is what it is. So Jess, wrap up.
Thank you everyone for attending the webinar today. If you have any questions or would like to discuss any projects that you may have, please do get in contact with us. Yeah, we're available online or via email or phone. So just get in contact and we can design that network for you. So just want to say thank you very much for myself and David and for everyone who attended today.